You can have like a XY table, R theta table, who knows what, comma, who knows what table. It's really just boils down to the same thing. It's just plug and chug. So if I pick a value to plug in, when I put a 0 in, what do I get for that part?
0.
0 plus 3 is 3. So that's 3. When you plug a pi over 6 sine of pi over 6 is 1/2. Half of 4 is 2 plus 3 is 5. Plug in pi over 4 into sine of pi over 4 is... Yeah, and then the 4 and the 2 cancels, you get 2 root 2, which is about 2.8 plus 3, this should be about 5.8. Pi over 3, that'll be the root 3 over 2 times 4, so that's 2 root 3.
6.46.
Yeah, it's about 6.5. And you can see when you're doing this, there's really no reason to go past the 1 decimal place, because doing this by hand, especially if you're me, you can't get much more precise than that. And then pi over 2, sine of pi over 2 is 1, so then you get 4 plus 3 is 7. And then what's really cool that happens here, you know what sine does, starts off nothing, goes up to 1, and then goes back to nothing again, right? So it's going to go exactly back through this.
In reverse.
And when you do the reference angle, you just relate it right, so that's 6.5, that's 5.8, that's 5, and now at pi, sine of pi is 0, plus 3 is 3.
3, yeah.
Is that cool? So I will accelerate that a little bit. Then you come over there, pi over 6. I'm in the third quadrant now.
So it's negative.
So if you do this way, it's kind of nice, but you just have to realize where you are as you're doing this. So all my sine values will be negative, exactly. So sine pi over 6 in general is 1/2, in the third quadrant it's negative 1/2. Times 4 is negative 2, plus 3 is 1. Then you're going to get 3 minus 2 root 2. Same way you got 2 root 2 earlier, but 3 minus 2 root 2 now should be about, I think it's 1/2, right? Remember correctly? Negative. Is it negative yet? 3 minus 2 root 2, no.
It's 0.2.
0.2, thank you. The next one will be negative 1/2.
Yeah, negative 0.5.
Pi over 3 will be root 3 over 2 negative. So you get negative 2 root 3. 3 minus 2 root 3, do it in the calculator. That frantically you must. You get negative 0.5 roughly. And then 3 pi over 2, which your sign is most negative. Right? So it'll be 3 minus 4 negative. And then this just goes, builds right back up. Yes, ma'am.
And when you say arrow, you just mean approaching pi?
Yeah, they're all reference angle except that last one. That's all I meant. I'm kind of developing this as I go for myself. You guys can use it if you like. You can make one giant table with all the actual angles, not reference angles, however you want to do it. All right. So let me show off my shortness there for a second. I've got all its values here on this paper too, so don't freak out. Yes. We just came.
You don't have to.
What's up? What kind of handout?
So you don't have to include that.
Oh, this thing here? Alright, let's see.
5 pi over 3. You need 5 pi over 3.
Bless you.
Yeah.
Just round it up. 5 pi over 3. This is 5
All right.
pi over 3. I don't have to actually do this because this is already here. This is 3 pi over 2. This would be 3 pi over 2. This would be 7 pi over 4. This would be 11 pi over 6. And this one would be
All right.
5 over 6.
So here we go. If you weren't here last time, you were just having a good day. So fun. So the way to plot this point, this tells you how far to turn away from due east. Right? And we want to go, in this case, we're going to don't return at all. We want to go out 3, so I don't know how you establish. I need to go out 7. So if I can make a whole sentence. So if I make 1, 2, that'd be 1, 2, 3, 4. I can count. So, and here. Finally. That's awesome. Okay. Yeah, you can almost not see that. All right. So 0, 3 would be 0. I don't want to turn it all. I'm going 1, 2, 3 out. There's 0, 3. Pi over 6, 5. So now I want to look at pi over 6 and go out 5. So 1, 2, 3, 4, 5. Where am I at now? Pi over 4 is 5.8, so 5.8 is 1, 2, 3, 4, 5.8. So right there, I go to pi over 4. Pi over 3, 6.5, so now I got 1, 2, 3, 4, 5, 6.5. Pi over 3 right there. Bam. Pi over 2, you could just look there, Jim. Okay. So pi over 2, I want to go 7. That should be 1, 2, 3, 4, 5, 6, 7. There I am. Cool. And it's just going to come right back in at the same trajectory. So here it's going to be here, here. You guys see what I'm doing here? And all the reference angles are going to be the same. So here it's back to 3. Oh, too much. 3. That's better. How do we know so far? Hopefully you won't use purple pen when you do this. So you can erase. So I got to do quadrant 2. Now quadrant 3, here's where things get a little freaky. When it gets to negative radii. Yeah, exactly. So pi over 6. So you can kind of, this is the 12. So here's pi over 6, pi over 4, pi over 3 reference angle. And then this will be 4 pi, 5 pi, 6 pi, 7 pi, 8 pi over 12, which is my pi over 3, pi over 4, pi over 6 reference angles there. I like this method, it makes it much easier. So this pi over 6 now I'm at 1. So I'm right here. Then I'm at 0.2. Yeah. Then I'm at negative 0.5 at pi over 3. So at this pi over 3, whoops, there I am. This pi over 3, I'm at negative 0.5. So I'm actually going to go back this way, a half. Right there. You guys with me? So at this pi over 3, in the third quadrant, I want to go back a half. Yes, ma'am?
So, what this is r equals 3 plus 4 sine theta. And these are the coordinate points for this equation.
That's right.
Is it a function? I guess you call it a function? Is that?
That's where things get a little more difficult.
Okay.
We're not there yet.
Oh, okay. But,
It's okay. But that's an excellent question because we talked about, now of course, go back to when you first learned graphing XY, graphing on a rectangular coordinate system. How long before they actually said rectangular coordinate system for one thing. How long before we talked about what a function was in relation to a graph?
They just kind of
A few semesters in,
Yeah.
right? So we're not quite to the point yet where we're ready to decide. But that's an awesome point. What would a function be in this case when one of my axes are actually kind of like this rotation thing? How would I define a function? I can't just go, well, it doesn't pass over. No, it doesn't hold anymore, right? So it's got to be some other way to define what a function is. And in this case, one way to kind of know that this is a function is the fact that I can solve for r directly, for one thing. But is that good enough, or does that even come into play in general? We don't know yet.
Well,
Right?
you
If
know.
it didn't
You
do
know.
that, huh?
You know. We don't know.
Exactly. But
You're
that's
not
certainly a
you're not
function of
telling
theta.
us.
I'm not telling you now.
Okay. That's all I wanted to know.
Yeah, f of theta, yeah. So that is a function. And then finally, at 3 pi over 2, so I'm going to face this direction, but go back once, and I'll go back to there. Is that cool? So face this way, and go back one. So whenever you got a negative r output, you just face the direction and go backwards from there, whichever way you happen to be facing. So I'm facing in this direction, I'm looking towards here, and I go back one. Cool. And now it's going to come back out. This pi over 3, it's negative 0.5 again. So I'm looking towards here, and I'm going to go back a half. Pi over 4, it's 0.2. So pi over 4, now I'm out here. It's 0.2. So I got to keep in mind that I went like this. Might as well draw that now, so I don't get lost. It's the connected dots where there are no numbers next to the dots. So it's kind of like, here's a cloud, what do you see? And that's seen in short circuit, what do you see? And then, where am I at here? I left off here. Pi over 6 is 1. And then I'm back. How did I mess up so bad over there? This pi over 6 was supposed to be 1. Oh, I didn't mess up over there, I messed up there. Good job. So here I am. This neat, sort of like the shape we got last time, except it's got this extra little feature that goes inside of itself. Funkydelic. And as it turns out, anytime this number is smaller than this number, you will get something that goes back on itself like that.
What number is smaller than what number?
If the first number is smaller than the second number. In fact, if you look in your book, page suspense. Page 552. There's a situation where we're in there. I made A less than B. I made A 3 and B 4. So then I was certain to get that little inner circle there. If they're the same, you get that awesome cardioid, better known as the butt graph. Then you get the, he's gotten slightly heavier, so he's sinking into the couch a bit. Graph. Yeah, limbason. Dimpled. And then the convex limbason is when A is greater than I. This gets a little more technical than we need to get here, but what we want to do is, in general, your normal circle, your non-translated circle is r equals a, which is beautiful. It only makes sense. The definition of a circle is all the points that are an equal distance from the center. So if you just set radius equal to a constant, you get a circle. Does theta matter? No. So theta doesn't care. Every single theta I go to, it's the same r. That ends up with a circle. Then we got these two that we know. A sine theta is on the y-axis. A cosine theta is on the x-axis. That last one, they put it in there because it's curvy, I guess. I don't know. But the spiral, r equals a theta. So that one's kind of neat. As theta grows, so does r. So as theta grows, you're just going to keep spiraling out more and more.
One that's like everywhere.
No, it's not a Archimedean spiral, or even a logarithmic spiral. It's just a spiral. It's not one of the special spirals. It's a special spiral. That's why it's all sense. Now these are the ones that are really nifty. And if you really pay attention, this is interesting. If n is odd, it's got n leads. So you'll notice for like A cosine 3 theta, it's got 3 leaves. But A cosine 4 theta, it's got 8 leaves. Now, what do you think is going on there? Why? It seems a little unfair. It gets twice as many if it's even as it does when it's odd. This one actually has the same number of leaves. Well, actually, they both have infinite leaves if you go far enough. It's just that its other 3 leaves are right on top of the leaves that have already been drawn, whereas these are a little offset each time.
The starting point of the 7% waves?
Sort of.
Like the one says.
But do you see how it's independent of sine and cosine, depending on, it just all depends on odd and even. Right?
It has something to do with the square root.
Like a sine, how do you think a sine 3 theta would look? What would be the main difference?
Be on the Y.
It would probably be, yeah, right? This guy, cosine likes x, but sine likes y, so it would probably turn around. Right? And how could you check that? I don't know. Maybe play with the calculator a little bit. So first thing you got to do, go to mode, and then set it to Polar. P-O-L right there. So go to mode, and then get that bad boy over to Polar.
I haven't seen it before.
Make sure you're also in radians. So now if you hit y equals, it's going to give you r's. So let's try this. Let's do 6 sine theta. I think it's, I'm sorry, 6 sine 3 theta. Let's do what we just said. Let's see what happens to this. Now let me point out a couple things to you. Everybody hit your window button.
It's a butterfly.
I'm really curious. I think most of you should say this. Does everybody have like 0 and 6.28?
Yeah.
What's 6.28?
2 pi.
2 pi. I love it. So if you don't have that, make this 0. You can make this 2 pi, and it just changes it over. Theta step is how far apart it calculates. Because what the calculator does is it actually does make an XY table. In this case, it makes an R theta table. So if you make this too big of a number, it's going to calculate 1, and it's going to turn, and it's going to calculate and connect it with a straight line, and that's not going to look like what it's supposed to. So about 0.13, whatever the hell that is. What is that times pi? I don't know. What is pi divided by 12? Let me see. All right, so that's pi divided by 24. So they just want one extra step. Sweet. Okay. So let's try this out. Where are we at, sorry? Oh, just make that normal. 10 to negative 10. Why did I make x min? Did I just do that on top of x min? I did, didn't I? I did. I suck. Make that 0.13. X min should be negative 10. My brain keeps hearing me say x min. Alright. So we were right. It just turned the other way. Kind of nifty. Anyway. So, I mean, this is a place where I think you guys might actually get your calculator out and just play with it, maybe, possibly. Like I did naturally, because I'm a complete geek at heart. My favorite play toy when I was little was a calculator. I don't know why. Back in the day when they're all just red letters on there. If you put in here sine, I don't know, 10 theta. Now it looks a little crappy because my step, I got to make my step better. You guys see how crappy that looks? I mean, it's crappy in 2 ways because it's a little bit, I can't really see what's going on. But this normally, when it's got these big, these sudden turns, it's telling me my step is too big. I'm not getting enough resolution. So if I make this 0.04 maybe, it's going to go a little slower because it's got more stuff to calculate, but it's going to look a lot better now. And of course, how many leaves does this thing have? 20. Twice that because it's even. So if you count in here, it'll have 20 leaves. Woo! Dude.
How did you get a better resolution?
Second. Oh, better resolution is you change the theta step. The trade-off, of course, is it goes with it. So if I make it 0.01, it's going to go noticeably slower. There we go. Oh, what have you done?
I just came out to 60. Why stop? I don't know, 3.
Stop. Stop.
I did 1,000.
No, because
Oh, I killed my calculator. That's different.
it's got 60 things. I have 20 things.
It's going to have an animation of smoke coming out of it. All right. So,
Uh-oh.
I mean, this is where you just start playing around, hopefully. I mean, what would happen if you added sine 3 theta to cosine 4 theta? What would it look like? Right? You can just start playing around. So on one hand, I'm obviously going to give you this kind of paper on the test. You're going to have to come up with the points and do it by hand. You can check yourself with the calculator. But on your own, just play with the damn thing. And what I keep wanting to find is, anybody ever play with that game Spirograph? Where the gears within the gears, and you put the pencil in and it would rotate and make all these. Some of you know what I'm talking about. They have like I've got to find it. I found it last semester. They have an online like applet, little Java thing that'll do that for you. You choose the size of the gear you want to use. It's really cool. Just got to find where it is. Is there any questions while I got this up here? Any questions about the calculator? Yeah.
What is theta? Oh.
Theta's right there.
Yeah, I'm not finding it.
So you hit mode, make sure you're in POL. Oh no, yeah, that's right.
I tried it with X and it was very not correct.
Where do you go to change?
I'm already in polar.
You're in Poland? That's strange, because it isn't. Oh, so maybe it might actually be okay. Where's your X here? Oh, I see. You're using theta. It's an awesome question. Units, very good. I have no idea what theta is.
Well, if you did after
You would think it'd be somewhere a little bit easier to get to. Oh, good luck. Okay.
Good luck with that.
All right. So, any questions on that? Oh. Oh, the London skate. What's the history of that name? You know, one thing I want to do is I want to develop a history of mathematics course. That would be awesome, because that would kind of force me to do some of the research. So I've researched a lot of things already about like why the square root symbol is the way it is and why we chose certain words for things and so forth. But there's stuff like what you just said that I don't even think about to look at. That, you know, that looks like an infinity symbol. At some point in my life, I was told why it's given the name it is, but I have completely forgotten why. They seem to be, but they actually have reasons behind them. Yeah. And very often you'll see like other things that have that as a piece of the graph, and they have this a word that kind of looks like this in their title. So they, you know, they exactly the kind of like root words of some other.
It trips me out. That looks like a flower.
I know, man. But it's not quite as nifty as Fibonacci.
Yeah, that's true.
Not quite. Okay, so 8.2 is basically going to be like that. It's going to be graph these things. And let me give you a couple of weird examples that you can't do in the calculator. I think I've already said this one. You running? Yep. Okay. We already looked at this. Yeah, we did look at this one. Like theta equal to pi over 3. You can't do that one on the calculator, right? You can't solve for r because r is not there. But who remembers what that comes out to be? And think about this. What doesn't matter here is r. And so if I have an equation like x equals 2, what does that look like? Careful how you draw it. X must be 2, so x cannot change. It can't go left or right at all. It must only go up and down. And do you see what values of y does it take on? All of them, because y is not constrained. R is not constrained, so what values of r will this take on? Everything. But theta must be locked at pi over 3. So I've got to be facing that direction, and r can be any positive or negative, so you just get that one. Same exact reasoning. All right, one axis is held constant. In this case, it's the rotational kind of axis. And the other one can take on all the values because it's not constrained at all. It can take on all values. Okay, may. Yeah. Oh. Yeah.
I think I figured out why it's the order of the points are the way they are. Because you can't subtend an angle without a distance. So
Yeah.
you need a line.
Because you could, in fact, earlier I just did that to make it a little easier. I went out like 5 point something and then I rotated. Yeah. But what I'm talking about is it would be really difficult when I was first introducing the idea of having somebody walk. It's much easier to have them turn first and then walk. If I make them walk and then I say, now subtend an angle of, what?
Right.
It'd be much easier to have something that would just, I turn this much and now I can walk this far. Right? But you're
With
right.
that analogy,
I
that
can
works.
go out and then rotate by an angle of so much. That works just as well.
Yeah.
Exactly. I love it. Cool. Okay. I think my point was more just theta is normally thought of as the input variable. Okay. So that's section 8.2. Let that one be not too evil. Right? Shouldn't be too terrible. Any questions over anything? Yeah. I did. In fact, I replied to you right when you sent me the email. No, about the, that's the statistics one. This one I haven't put up yet. Right. Let's see. So I'll let you guys see as you get into that if you have any further questions. See where I put you at. Oh, I left it in my office. It's too bad. There it is. All right, so we're getting into. Yes, ma'am. Yeah, sure. Yeah. And actually, while you got me thinking in that direction, quiz. This is not Elizabeth's fault, by the way. I was going to say this eventually. I might as well say it now. Quiz on Wednesday. Basically from double angle formula through solving equations with trig functions, right? So it's, hold on, let's say it. Yeah, 7.3 through 7.5.
Like in 2 days.
2 days?
Yes, this Wednesday, yes. Because we finished that last Wednesday. So whenever you give a quiz, it's always on the stuff that's due that day.
So will there be another quiz before the class starts?
I don't know yet. We'll see you as we get closer. Probably. Which one are we looking at? 55? So we have... Okay. Oh. Oh, the one online is a minus. All right. What I'm about to do would be the same thing. Well, I'll put a... So, what's telling me how far to go in this problem? If that wasn't there, I would just take this down to 2 theta and stop. But of course, that's there. So I need to get everything to have the same angle so that they kind of work together. There might be some quadratic stuff here possibly, or there might be something else. I need to have those angles, these input variables to be the same. Not twice theta, 4 theta. They all have to be theta. So let's start with this because this is the one that's what the formula is based off of. And this is where you have a choice of which way to go. Considering cosine theta is in there, which choice should we probably use? Should I use, remember cosine 2 theta is this, or it's that, or it's that. So which one should I use? Probably the last one, so I don't introduce some crazy sign out of nowhere that I don't need to. I definitely want the one that's got cosine in it because there's another cosine running around. And it looks like it's probably going to be some kind of quadratic thing that I might be able to factor eventually. So I want everything in terms of cosine theta. So this guy I can make directly into 2 cosine squared theta minus 1. Oh, let me make this. I don't want to do that to everybody. I make this a minus so it's a like number 55. And then this one, what would that become? If cosine twice theta is 2 cosine squared theta minus 1, cosine 4 theta. No, see, this is where we focus too much on the wrong thing. Cosine 4 theta would be cosine squared 2 theta minus sine squared 2 theta, right?
Right.
Yes.
So what changes here is just that's 2 theta. So that's, oh crap, so now I've got to go. So this guy agrees with this guy now, but this guy does not anymore.
I don't understand why that's 2 theta. As opposed to...
So in general, cosine of something, let me say this, cosine of twice something is blah 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 2 cosine squared of that thing minus 1. So whatever I put here, what happens to it here?
Oh, it becomes half of it?
Becomes half of it. Now if I just gave this to you, I wouldn't blame you for thinking that goes with 2, so if we make it cosine 3a, it's suddenly 3 cosines. We know, but we know better. We know where this piece came from. It came from these. Breaking up whichever one of those we wanted to, right? And what happens here, this is half of that. So that's going to carry through all of these. This will be half of that. So that's why that's 2 theta, because that was 4 theta. That's why those are called the double angle formulas.
So the coefficient is 2 because it carries out, it goes out? Is that, no? Is
The
that what you're saying?
coefficient,
Not-
are you cool with this step here?
Okay.
And then of course this step is a little cosine squared minus 1 minus cosine squared. So you get 2 cosine squared minus 1. That 2 is purely because we broke that up into 1 minus cosine squared. So this 2 has nothing to do with this 2. The name kind of gives it away. This angle must be half this angle. End of story.
It was cosine 6.
So if I had cosine 8 theta, this would be twice cosine squared 4 theta minus 1.
Do you want to show our work when you do this? Or no?
If you show this,
Uh-huh.
that's fine.
Okay.
Cool. because that's the direct application of the idea. Yeah. Now what do I have to do here still? Brought that negative through. This is cosine 2 theta squared. And cosine 2 theta is 2 cosine squared theta minus 1. Looks awesome. So then you got to FOIL this out. Right, so we get 4, so you get 8 cosine 4 theta. Right, cosine squared times cosine squared. Minus 4 times 2 is 8. Cosine squared theta. I have faith you guys can FOIL that out, and I'm just doubling all the stuff that we get when we FOIL it out. Plus 1, so plus 2, because I got to double it. These go away. That's gross. I like it.
And the book says like we have to solve it like by using the sum to the product formula. We on 4.555.
Yep.
It says like to solve it through the sum to the product formula.
That's number 55.
Wants us to use
7.5.
Oh, cool.
Yeah, I think you.
So they actually told us what to use. I love it. It's even better.
2 sine.
So those sum the product formulas were these guys. These are some that I don't make you memorize because you can tell I don't have them memorized. All right, this is obviously the one we don't want. But hold on. So if I look back here, I've got cosine 4 theta, in this case minus cosine 2 theta, equals cosine theta. So here I've got cosine of something minus cosine of something else equals this business.
Same thing. Just the cosine first.
Okay. So that's obviously not the first thing I would think about. Of course, I should have read the directions. This is the first thing I would try, and you very quickly get into something that's not even really quadratic. It's kind of getting pretty disgusting. I got this 4th power I have to somehow deal with. And you could do power reducing from here. But this is getting kind of unwieldy. It's getting a little bit too big. So I looked at this one for this problem here because I got cosine x minus cosine y. So I can replace that with that. Now let's see if this looks any better. So here we've identified x to be 4 theta and y is 2 theta. So cosine 4 theta minus cosine 2 theta equals negative 2 sine, what's x plus y going to be? 6 theta. Divided by 2, so you get 3 theta. Sine x minus y. 2 theta divided by 2 is just theta. So let's see what that gets me here. I get negative 2 sine 3 theta sine theta equals cosine theta. Doesn't look all that much better to me, but not really. But it's the only thing I've got I could try. Now, you could play around with this. So this here is going to be getting us into something that I really don't want to get into. We could break that up, but it's getting a little bit too large. If we do like the hint suggests to use a sum to product formula, the only way I can really use the way it's given to me is that one. Now notice you could add this over, possibly, and try it with they give us a cosine x plus cosine y option. Yeah, and that's all in terms of cosines. That seems a little bit more feasible. But then I still have this guy to worry about. Well, you know, might come out all right. So for you, I might try to add that over and apply it possibly. Or maybe play around with this. Maybe this does boil down to something better, right? But I would try to move that over first maybe and see what that comes up with. Because I don't think that would do much for us. Now your actual problem for the rest of you guys in the book, it's got a plus there.
Yes.
So then I can use the cosine x plus cosine y one directly. And that's the one that's related already to cosine. So I think the book one's a little bit easier in that one. Yeah. So here, before I get too deep in this, let me backtrack here for a second. Let's make this a plus like it is in the book. Okay, so that's the thing I can apply directly. This is one of the ones I don't make you memorize. You just have to be able to use it if they say to use it. So now I can see x is 4 theta, y is 2 theta. So I get, this becomes twice cosine x plus y, 6 theta divided by 2 is 3 theta. Cosine of theta. So that looks a little better already because that'll at least factor when you subtract the cosine theta over. And then you just have to... Well, let me go ahead and do this over. Oops, yeah. Take out a cosine theta. Now, why is that not that bad? This is almost done. Because now cosine theta equals 0. You get answers from that. Or twice cosine 3 theta minus 1 equals 0. You get a bunch of answers from that. Maybe we should take a second to remember how this works. What do I get here? What's the base answer here?
2 cosine 3 theta.
Yeah, what cosine of what angle is 0? Pi over 2 or 3 pi over 2, but they are, of course, exactly pi apart. So if I start at pi over 2, what do I want to put there to capture all of these?
2 pi.
Not 2 pi, I don't have to go a full rotation, I want to go half rotation. Pi.
Okay.
So from here to here, just make sure everybody's okay, because I hear a lot of whispering and looking in that direction. We just applied that directly.
Oh my God.
Here, how do I solve this one? Add the 1 over, divide by 2. What's 3 theta got to be then? What cosine of what is 1/2? Cosine of what angle? Give me radians. 1/2. Pi over 3. Or cosine of pi over 6 is going to be root 3 over 2. It's going to be the bigger one. Where else is cosine positive 1/2? At pi over 6. Sorry, what is this? Pi over 3. Or, yeah, 5 pi over 3. Can I do a half rotation or something and capture? This is the one where I have to do the full rotation around from each, right? So plus 2 pi k. How do I finish this problem out? Because I don't have theta by itself yet. Just divide each of those by 3, not a big deal. Because pi over 9 plus 2 pi k over 3. Okay. So let's hopefully, if you pull that over for your problem, it becomes possibly this simple. We'll see.
So how do we get like the pi over 3 from half to cosine 3 pi equals to half, and then the next step 3 pi equals to pi over 3?
What does this angle have to be to make the cosine of it 1/2? It's got to be the bigger angle, the pi over 3 angle, so that you got a small little x piece, right? So that means this angle must be pi over 3. Or it could be in the 4th quadrant, 5 pi over 3. And then how do I get all the answers then? I start doing the rotations, the 2 pi k from each of those. Yeah. Then finally I divide by 3. 3's don't cancel, it become 9. Yeah.
Thank you.
Okay. That was neat. So in that section, the thing to learn there is to read the directions that tell you exactly what set of formulas you have to use. And they're not ones that made you memorize. Because I have not memorized them either. Yep.
I emailed you about an example in 7.2.
Yeah, I got your email, Emily. I don't think I could explain this over email. So 7.2.
Yeah, it was just like first or second example.
Oh, no, I did email you back.
Yeah, it was about factoring, but I don't understand like the steps in between. Like I understand what the entire thing is doing, but I don't understand what they did in between because I just don't know what's going on.
In between, how do you mean?
So
we're looking on page 500, the proof for the addition formula for cosine.
Because they just kind of just skipped steps and I didn't understand what's going on.
Well, you take try to make an angle half of it and then divide by 2 and plug into the formula. Same questions, 7.2. Like you divide the angle by 2, like trying to make it half, and then for addition and subtraction formula.
I don't understand.
Because well, I'm talking about.
We have 2 different things going on.
Are you? You can go ahead. So it's the first example, the proof of addition formula for cosine.
Yeah.
And I guess I understand taking the square root, and then I understand the first part. And then
So the whole thing here is it's based on distance formula. Distance formula is why there are square roots there in the first place.
Right.
Because the distance between 2 points is that. I don't know if that looks familiar to anybody. It's basically Pythagorean theorem. Okay, so they use that and they plug in there the values, the points written in terms of cosine and sine. Right? And they say, if you read through this proof, they're basically saying that these 2 distances have to be equal. So they set the 2 distances equal to each other. The first thing they do is square both sides. Because both sides have square roots. So square them away. That's where the square roots go. Because you get square root of this equals square root of something else squared to get rid of your square roots. Then they FOIL this stuff out. Just FOIL it out. Get your like terms together. That's what they do in the next step. And then they look for identities. They have a couple of cosine squared, sine squared identities. They can make those become 1, so that becomes nice. So it's when you're trying to look over a proof, which we should all be doing, it'd be awesome. Any proof I don't actually do in class, and I do a lot of them in class. This is one I didn't really talk about in class too much. Not like this anyway. I had a different approach. You just attack whatever is written, just attack it. If it's something squared, FOIL it out. Get your like terms together. And just kind of see if they got the same thing you did. I mean, that's really all they're doing is they're just brute force attacking these things. Right? FOIL it out, get your like terms together. So,
Okay, yeah. No, that's good.
you just got to try it out on your own.
I did.
Oh, okay. All right.
Okay.
Any other questions from homework or? Yeah. 64. So far. Oh, cool. This is exactly the kind of problem I would give you. What's it say?
It's the spring displacement lens. It's the vibrating spring.
Oh, where am I looking at?
We don't want the one you're gonna give us on the top.
Shoot. Well, that one I'll do in a minute. Because I got your attention. That's actually from the review. On one page too far. Sub 5 is the vibrating spring. Oh, cool. I think I showed you guys this. I can't remember now. If you graph this in your calculator, you'll get something that looks a little bit like this here. It's kind of cool. And the top and bottom are going to be basically that. That's mine. What's in front of a sine is its amplitude, right? And the amplitude here is e to a negative power. What is something to a negative power going to do? It's going to get smaller and smaller and smaller. So it's kind of, that's what we call dampening. If you pluck a guitar string, it's not going to go forever. Because of the air and everything else, and everything's kind of taking away all that stuff, the friction happening, it's going to slowly die down. So what are they asking for? Let's see. Find the times when the spring... Oh, so we're looking for these times. So a guitar string is not a bad example, but this is a true spring. And I pull that spring and it goes, wow, wow, wow. All right? So I want to know exactly when does it go back to its normal position before I pulled it and let go. And over time, it's eventually going to calm down, right? That's the first thing you do with the slinky, and then eventually it gets all twisted on itself and you can't use it anymore. Like young Jeff. Well, a weekend after I got my slinky, I killed it. Like. So you're trying to solve this equation for this. You're trying to solve this equation here for t. Now the nice thing is it's already factored. This times this. When is this equal to 0? When is that equal to 0? When t is 0, I get 4.
When t is one.
When t is infinity, which we won't get to, right? So that's too bad for us. This doesn't give us any answers, right? A number to a power can never become 0. Period. You can't take a number, raise it to a power, and make it 0. You can't. Okay. So that's not going to give me any answers. I'm going to get all my answers here. So now I just got to solve this for t. So what's got to be true about 2 pi t? What's got to be true about that to make sine of it 0?
0 and
0 plus 2 pi k. Right? Where k is what? Be more specific. K is 0, 1, 2, and it's actually negative 2, but we're going to think this all starts at time 0. You with me? So k is 0, 1, 2. So if you solve this for t, what do you get? T equals k. So what are the times? 1 second later, 2 seconds later, 3 seconds later, 4 seconds later, all the whole numbers. At 0, it's obviously right before I've taken this thing out. It's at its equilibrium position. Then I do it, and I let go. And then 1 second later, is there again. Is there again. Doesn't make that sound necessarily, but...
So what would the last number be? Would be 1. Or is this the answer t equals k?
This theoretically is infinitely long that it does this. In the real world, of course, it's kind of quantized. At some point, it's going to be stopped. So that was a good question. I like that. It's a lot easier than it looks at first. I mean, it's just simply theta equals 0. That doesn't give me any answers, and that's 0 when t is any whole number. Any whole number multiplied by 2 pi, this thing is going to be 0. You'd have to have a spring that's set up to follow this equation. Yeah.
Can you do that question?
Where are we at?
The one at the top.
Oh, yeah, sure. So now on to this, the one that I said I'm definitely going to have on the test. So it's just serendipitous for us that I looked at the wrong problem. Is everybody cool with this here?
Yes, sir.
So looking at this, what is sine of 2x? What is that? What's the only identity we really have for that? Good. 2 sine, cosine. So to figure out sine of 2x, I need to know sine x and cosine x. It's kind of funky. I know secant x, therefore I automatically know cosine. What's cosine got to be? 2 over 3. The reciprocal function, right? And now I got to do is figure out what the hell sine is.
That's a good too.
Yeah, I can set up a little triangle. Here's my angle. Cosine of the angle, let's make it x here. Cosine of the angle has to be 2/3, so where's the 2 go? Bottom, the 3 there. This is going to be square root of
1/9.
second. Oh, y though. That's the problem. Yeah, because some of these have y's in them, I think is the point. Where was I looking for this? Here we go. Yeah, some of these have y's in it. So unfortunately, this doesn't help me out at all in this problem here, because I won't have any y's coming at me. So I do have to do this step here. This will be what? Square root of 5. Well, 9 minus 4. So then sine x will be
Square root of 5.
square root of 5 over 2. No, over 2. 3. And now I just got to plug it all into that formula there. So it's twice sine over times cosine. So we get 4 root 5 over 9. Somebody do me a favor?
Yes, sir.
Figure out what the x is here. What's x? Here. Maybe in degrees, just to make it easier to think about.
We have to pick it out from the polar mode.
No, you just have to make sure you're in degrees and you'll be fine. We're not graphing anything, so it's okay to be in polar.
48.19.
What'd you get?
48.19.
Yeah. We got like 48.19. Now look here, this is sine 2x, right? So what's 2x? It'd be the inverse sine of this business here. So what's the inverse sine of that business there? No.
No, I was previous.
41.8.
I get 83.62.
262. Then this should be divided by 2.
Yeah, it should be 41.
And then it's 41.81.
Oh, I see.
I got 41.8.
Yeah, I got 41.8. Oh, you got 41.8 here?
Let's see.
Wrong. Anyway, I was hoping that'd be nifty to look at, but
48.18. Yeah,
that's weird. I gotta think about that. Oh, it's because of the way the inverse
it's
sine.
dyslexic.
Of course, I'm being stupid. Yeah, this would be 97. I gotta think about that.
So the answer is 4 squared by 9.
That's there. Yeah, think about that. That's not the way it should have come out. It's freaking me out. Alright, let me think about that. Anything else from the homework? Yeah. 7.3. Oh yeah, all right.
What number?
This is page 516, number 102. So we want to figure out the length of S in terms of A, B, and it says, hint, use the law of sines. So they already tell me the length of S. I'm just trying to show that the length of S is this. That looks very interesting, the top there. Does that look interesting to anybody else?
Mm-hmm. It looks like a log.
Yeah, it looks like part of the law of cosines, actually, which is interesting. But their hint is to use the law of sines. Huh. So, I want to figure out the length of this. So I've got this triangle here that's got it as part of it, and this triangle here that's got it as a part of it. So for example, and I've got, of course, this whole triangle here. So if I look at just, let's see.
So
I've got this triangle here. And I've got this triangle there. All right, so I'm going to call this little triangle 1, 2. And the whole thing we'll call triangle 3. That makes sense. Put 1 and 2 together, you get 3. So, and I've got these x's, but I also have, like 2x if I ever want to use that also, right? Because I've got this 2x across from this side if I want to use that. But in this angle here, in triangle 1, I've got, for example, what's the ratio I can set up here?
Sine B over.
Yeah, sine B over S. And that equals, now what other kind of ratio might I want to set up there? Now I've got to operate just in this triangle here, right?
Sine C.
we have to use a 2 sine.
Now this is kind of weird. This angle here is going to be a little bit strange. So the problem is I have 2 unknown angles down here, really. But I know this is angle A. This is angle X. So this one's got to be basically, 180 minus A minus X. That might come in handy. Or minus A plus X, one way or the other. And of course this angle here, here's the kind of nifty thing. If that's 180 minus A plus X, that's just A plus X. Now that's interesting. And again, the really nice thing about problems from the book is, of course, you can kind of pay attention to the section you're in. On a test, you can't do that because I don't have it by section. But this is in the section with double angle, half angle, and products to some formulas, right? So notice the ratio I can make now. Sine of A plus X over A, right? Now you can do a similar thing for the other side. I don't have anything. I got cosine X here. 2AB cosine X over A plus B. If you try to do something for this triangle here, what would it be? I could say sine A over S. Now here's the neat thing. Let me see if you guys can do this. I could have done what we just did here, from here to here. I could have done it the other way, couldn't I? What's another name for this angle here using the stuff in this triangle?
See,
This is angle B. This is angle X, so this must be 180 minus B plus X. Same kind of way. So then what must this angle be? This angle must also be B plus X. So I can say this is sine of B plus X over B. Now it looks like I should use here the sum formula for sine. Right? And do the same thing over there. Just got to follow that logic, see if that gets you somewhere. You know what's kind of guiding you is this. So if I do use that, what's the sum formula for sine? If I have like a plus x, remember sines that I used to do?
Sine
A plus sine X.
Plus sine x cosine a. So I got cosine x in there. Hey, I got part of what I want. This is sine b over s equals this business. I mean, you almost have too many ways to go with this. Because I can still look at the big triangle too if I feel like I need to. Well, like this could be sine of 2x over c. I really don't want to bring c into it because c is nowhere there. But that actually might be... probably not. I was going to say that might be the thing that ties this together, but now I'm thinking about it. I don't think so. So, I mean, this is a good example of you just got to take what you're given and play with it. Right? So we played with this. I think this is, there's not really too much more I can do. Now, what part of this do I not really want in there? It's like that sine x and sine a. But could I possibly use that? I could kind of rewrite this, and couldn't I use this to figure out another name for sine a? Maybe plug it in there. I mean, there's a few things you can try. And I feel pretty decent because we got to a point where we could at least apply one of the formulas from this section, right? That doesn't mean I'm in the right track exactly, but it means I'm in the right general ballpark. You set up. Their hint was use the law signs. So I use the law signs a couple times, and I'm going to play with both of these, right? Kind of keep an eye on what I want, where I want to end up. So what I would suggest is go ahead and rewrite this out and see if there's anything you can see between these two that would take you in this direction. Alright. I know it's less than satisfying, but it's just a problem where you got to play with it. Okay. Now if the only questions are out of like the last parts of the homework, that's awesome. Because those are the problems like this, which are just purely, can you play with this thing? Are there any other questions from chapter 7? Yeah, or 8?
18 on 7-2, or 7-3.
Seven 3, sorry.
Correct.
Oh, the tangent 15?
Yeah.
So that kind of immediately makes me think of this, because I can do the tangent of 30 degrees. So now you look up the formula for this. Tangent theta over 2.
Sine u over 1 plus cosine.
Well, a little more directly.
1 minus
Yeah, here we go. Yeah, cool. I got you. So you can either do the 1 minus cosine over 2. I'm sorry, sine. So there you go. That's one I wouldn't make you memorize. But I know cosine at 30 degrees. I know sine at 30 degrees. Right? So this is tangent 15 is tangent of 30 divided by 2, which is 1 minus cosine 30 divided by sine 30.
I just looked up the wrong formula.
Oh, okay. Not hard to do. There's so many.
Same exercise, sir. 21 question, cosine 165 degree. You can make
Do it again, sir.
Oh, 21.
21.
514. Same page.
Okay, so then you say, what's twice 165?
330.
330?
Okay.
And that's an angle that I know.
Right.
So then I look up the cosine of theta over 2 formula and do the same thing.
Sometimes you divide, sometimes you multiply, right? The angles, whichever works.
Whichever works, yeah. Normally this is the one that's going to work. Yeah. Okay. Anything else from chapter 7 or 8? Okay. So, we're going to get into section 8.3 and 8.4. You guys want to take a break first? Yeah. Come back at like, come back at 4:15.
You guys don't steal my race or calculate any stuff.
Oh yeah, you emailed me. I'm pretty sure I meant to say E5 though. Yeah, I know. I'm pretty sure I meant to say E5 though. Because I had a different assignment there where it was every third one, then I changed it to every fifth one. And I just forgot to change it.
Oh no.